Okay, today we are going to talk about directional derivatives and the gradient. So below we can see a graph of f of xy equals 4 minus x squared minus 1/4 y squared with the point 1, 2, 2 plotted. So you can see that point here, the 1, 2, 2. And if we ask you to find the partial of f with respect to x of the point 1, 2, we could go through and do that. So I would like you to hit pause and I would like you to find the partial derivatives with respect to x at 1, 2 and the partial derivatives with respect to y at 1, 2. All right, hopefully you had a chance to go through that. And let's start with the general partial derivative at any point xy. And the partial with respect to x would be negative 2x. So therefore, when I go and plug in that point 1, 2, we get negative 2 times 1, or just negative 2. And if we find the partial with respect to y, the general equation, we would get negative 2/4 y, or negative 1/2 y. And so when I plug in the point 1, 2, the partial with respect to y is negative 1. Okay, so what does that mean though? When we look at this partial with respect to x, and we say it's negative 2, what we're saying is that the slope in the direction of x from the point, or in the same direction as the x-axis, from the point of 1, 2, 2 is negative 2. So what we're saying is that this gives us the slope in the direction of the x-axis. And what we're saying for f, the partial derivative with respect to y, is that this slope would be in the direction of the y-axis. So in the direction of the y-axis, that slope coming off the point 1, 2, 2 is negative 1. Great. But what if we want to find the slope or the rate of change in any direction? What do? Well, that's where the idea of directional derivatives comes from. Okay, and so a directional derivative gives us the slope in any direction. Okay, and so what it says is that given a differentiable function and a unit vector, that's important, it's a unit vector. A unit vector, remember, means the magnitude is 1. AB, the directional derivative of f in the direction of u is the dot product of the vector valued function of the partial derivatives and the unit vector. So the notation that we have that you will see with this is this d subscript u. So this says the derivative in the direction of u. So it doesn't just limit it in direction of u. It does not just limit it to the direction of x and y axis, but it is the direction of u. And we take the dot product of this vector, and this vector that we have here, you'll notice, is the partial derivatives with respect to x and y. Dot product with that unit vector that we talked about, AB. Okay? Now, we could expand that dot product, and what we would get is we would get the partial with respect to x times a plus the partial with respect to y times b. Now, we can extend this to 3 variables as well. We could extend it even further, but this is what it would look like, just that dot product. Okay, so let's look at an example. All right, this first problem says, let's find the derivative in the direction of u at the point 2, 0. So this expression right here just says at the point 2, 0, meaning that's where we're standing. To find our directional derivative, where the function is f of xy equals x e to the xy plus y, and u is the unit vector in the direction of theta equals 2 pi over 3. So what I might do first is find my unit vector. And since we're in the direction of theta equals 2 pi over 3, my unit vector is going to be the cosine of 2 pi over 3 and then comma sine 2 pi over 3. And if we evaluate that, the cosine of 2 pi over 3 would be negative 1/2, and the sine of 2 pi over 3 would be root 3 over 2. So there's my unit vector. Now I need to find both of my partial derivatives, both with respect to x and with respect to y. So the partial with respect to x would be, well, it looks like I've got a product rule there. So I've got the derivative of the first times the second plus the first times the derivative of the second, and the derivative of the second is going to have a chain with that y. So there's my partial with respect to x. Now my partial with respect to y, I do not have a chain rule, a product rule in this one, but I do have a chain. So that would give me x squared e to the xy plus 1. Now I need to, since I'm not finding just a general expression for the directional derivative on this one, I'm actually evaluating it at a point. I need to substitute in that point 2, 0. So that would give me e to the 0 plus 0, which would be 1 for the partial derivative with respect to x. And then the partial derivative with respect to y would be, let's see here, plug in 2, we would get 4 e to the 0 plus 1, which gives us 5. Now, if I want to find the directional derivative in the direction of u at the point 2, 0 for the function f, I know I'm going to be doing the dot product of this partial derivative vector and the unit vector. And so what that looks like for me, in this case, the partial with respect to x at the point is 1, multiplied by the x component of the unit vector, so negative 1/2, plus the partial with respect to y at the point, which is 5, times the the y component of the unit vector, which is root 3 over 2. Simplifying that, they're both over 2, so I get that this directional derivative would be negative 1 plus 5 root 3 over 2. All right, so see what you can do. Hit pause and try this next example that happens to be in 3 variables. All right, so hopefully you had a chance to try this. And the first thing that I'm going to do on this one, again, is to find a unit vector, because this is currently not a unit vector. So looking at this, the magnitude of this vector would be 1 squared plus 3 squared, so square root of 10. So my unit vector in this case would be negative 1 over root 10, 0, and then 3 over root 10. Now I'm going to find each of my partials, and this time I have 3 partials, but the good news is I don't have to evaluate them at a point. We're just finding the general directional derivative. And so if I find my partial with respect to x, I would get 2xz minus yz. The partial with respect to y would be 3y squared z minus xz. And the partial with respect to z would be x squared plus 2y cubed z minus xy. Now what we can do is take the dot product of the unit vector and this partial derivative vector, which isn't written in vector form at the moment, but if we take the directional derivative of this f of x, y, z in the direction of u, that unit vector, we would get 2xz minus yz times negative 1 over root 10 plus 0, because 0 times that partial with respect to y is just 0, plus x squared plus 2y cubed z minus xy times 3 over root 10. Now really the only simplification that you might see on this maybe would be to rewrite each of these in terms of a fraction. I mean, they're all over root 10, So we could simplify this, distributing that negative to get positive yz minus 2xz plus 3x squared plus 6y cubed z minus 3xy, and then that would be all over root 10. So either one of those forms would be fine, but there's the directional derivative. Now, if we talk about these directional derivatives, the ones we've been working on before, the partial with respect to x and the partial with respect to y, are in fact directional derivatives. They're special cases, and in that, the partial with respect to x can be thought of a directional derivative in the direction of the unit vector 1, 0, or that vector I, and the partial with respect to y can be thought of as a directional derivative in the direction of j, or 0, 1. So they are in fact directional derivatives, but the idea behind directional derivatives is to make it so that you can move in any direction. Now, this leads us to our next topic. Let's talk about the gradient vector. So if we have a function z equals f of xy, and we know that we can take the partial derivatives of each of x and y, or with respect to x and with respect to y, then the gradient vector that we have is notated by this upside down triangle. This is often referred to as del. The del f, or the gradient of f, is the vector made up of the partials. In fact, it's what we've been using to find our directional derivative. So this vector that we've been finding, that partial derivative vector, is in fact what we call the gradient. Now, this upside down triangle f could also be written as a bold grade. It says grad of f, but it's the gradient. And the gradient of xy is a vector in 2 space. And if we extend that to 3 space, the gradient of f would be a vector in 3 space. Now, with this definition of a gradient, we can change what our directional derivative looks like, although it doesn't actually change the function at all. We would then take the dot product of the gradient and the unit vector. So this would be the slope at the point xy in the direction of u. So hit pause and try these examples using the gradient. All right, hopefully you had a chance to hit pause. Let's go through this. If we talk about finding the gradient of f in this case, we would really just be finding the partial with respect to x. So in our case, that would be the cosine of y, comma, and then the partial with respect to y would be negative x sine y. So there is our gradient vector. Now, if I change this into a unit vector, we know the magnitude of 4 plus 1 is root 5. So this unit vector that we have here would be 2 over root 5, comma 1 over root 5. And so my directional derivative in the direction of that u vector of f of xy is 2 over root 5 cosine y and 1 over root 5, let's do negative 1 over root 5 x sine y. And there we go. All right, try it on this next one and see how you do. Okay, my gradient in this case would be, let's see, we've got chain rule. So we've got the derivative of natural log is 1 over x times, 1 over x squared times the derivative of that, which is 2x. And for y, we would have z cosine yz. And for the z, with respect to z, we would have y cosine of yz. And there is my vector. Now, this one says we want to evaluate this at a point. So at the point 1, 1 pi. And to do that, I'm just going to plug in 1 for x, 1 for y, and pi for z. And so for this first one, I would get 2 over 1. This next one, I would get the cosine of 1 pi, so cosine of 1 pi is -1 times z, which is pi, so this would be negative pi. And then the cosine of yz, which would be the cosine of pi, which is -1, times the y value of 1, so this would just be -1. And this is not a unit vector yet either, so this would be the square root of 1 squared plus 1 squared plus -1 squared, or the square root of 3. So my unit vector here would be 1 over root 3, 1 over root 3, and -1 over root 3. And now we'll do the dot product of those two, the gradient vector and that unit vector. And therefore, the directional derivative at the point 1, 1 pi in the direction of u would be 2 over root 3 minus pi over root 3 minus 1 plus 1, because there's minus a negative, so plus 1 over root 3. And if I wanted to simplify that, I would get, let's do 3, minus pi over root 3. How'd you do? All right, well, let's look at some applications of the gradient. All right, so the applications we're going to talk about are relating to the two variables. That's all we're going to look at today, but they could easily be moved into the idea of 3 variables. So the first property of the gradient says that if the gradient is equal to the 0 vector, then the directional derivative of f in the direction of u will also be the 0 vector for all unit vectors. And if we want to prove this, I would simply say that the derivative in the direction of u of f of xy, I would start with the fact that we know this is the gradient of f of xy, dot product with that vector, u. And if we do a 0 vector, dot product with some other vector, then the result, regardless of what u is going to be 0 plus 0 or 0. So that directional derivative will be a 0 vector for all u. Now, this is the coolest application. What we know is that since vectors give magnitude and direction, the direction of the gradient is the steepest ascent, and the magnitude gives the slope of the plane in that direction. So, when we talk about the direction of maximum increase of f, we can find that by finding the gradient. And then the maximum value of that directional derivative is actually equal to the magnitude of the gradient. Okay, let's look at a proof that goes with this. If we have that directional derivative in the direction of u, and it equals the gradient at xy dot product with that unit vector u, if we go back to our definition of dot products, and it's been a while, we know that the dot product is equivalent to saying the magnitude of the the magnitude of the gradient of f of xy multiplied by the magnitude of u cosine theta. Now, what do we know about u already? Well, we know that this is already a unit vector, which means its magnitude is 1. So I'm finding the magnitude of something that already has a magnitude of 1. So I could rewrite this to say the magnitude of that gradient, parentheses, times 1 times the cosine of theta. Okay, well, let's think about the cosine of theta for a moment. Where is cosine of theta at its max? Well, the max of cosine is 1, and where it's at its max is when theta equals 0, right? If theta equals 0, this is a value of 1. And so really, I'm multiplying that by 1. So we can say that the directional derivative of maximum increase, the highest one we can get, is the magnitude of the gradient of f. So there's the proof for that. Now, use this proof. We're going to use this proof again, just we're going to look at it a little bit differently. Now, if the direction of maximum increase is given by the gradient of f, then the direction of minimum increase. If we talk about the direction of minimum increase, maybe another way of looking at that is maximum decrease. Where is it the maximum decrease? Well, as you can probably guess, this is going to be the gradient or the opposite of the gradient of f of x, y. And then the minimum value is going to be opposite of the magnitude of the gradient. Okay, and I'm not going to give a proof for that one as it follows very closely from number 2, but that's the idea behind the gradient. The gradient really does tell us what direction our maximum increase is. Where is it going to go up the quickest? And if we found the opposite of the gradient, we're going to find where it goes down the quickest. All right, the last one that we want to talk about, I'm going to scroll up. The last one that we want to talk about is this gradient vector. And this gradient vector is always going to be normal or perpendicular to the level curves or the level surfaces. Okay, so let's look at a proof of this, or let's talk about it for just a second before we look at a proof. Think about if you're on some path and you want to get off the path as quickly as possible. Do we keep walking in the same direction of the path to get off, or do you instantly turn and get off that path at a 90-degree angle as quickly as you can? Well, that would be the quickest way. Otherwise, we're going to stay on that path a little bit longer if we don't turn and do something perpendicular to where we're at. That's the same idea. So let's look at a proof of this. So let's define for our proof our surface to be the equation f of xy. And we're going to let C be a curve on the surface, some curve on the surface. And if we parameterize this curve, we might call it r of t equals the magnitude of x of t, comma y of t. Now, when we talk about a curve, a level curve or a level surface, remember that is some k value that is equal to the surface. So this is our level curve. So if we want to take the derivative with respect to t of this surface, f of xy equals the level curve, I want to take the derivative with respect to t, so I'm going to rewrite my function with respect to t. So I would be taking the derivative with respect to t of f of x of t, comma y of t. And that is equal to k. So I'm going to take this derivative now. And thinking about this derivative, we have a function in terms of x and y are both in terms of t. So we've got a chain rule that we're going to work with. And so my derivative here would be the partial of f with respect to x times the derivative of x with respect to t plus the partial with respect to of f with respect to y times dy dt. Oops, I don't know why it's doing that. Dy dt. And the derivative of k would be 0. Well, look what this gave us. Let's separate this just a little bit. Let's take these two pieces. If we take this piece here and this piece here, Notice those are my partials. And then if we take this piece, the dy, dt, dx, dt, those, I'm not going to write any different, but those are my first derivatives, equals 0. And so really what I have is the gradient of the function dot product with the derivative of that position function, and it equals 0. Well, what does that mean? We know that if the dot product is equal to 0, then they are in fact perpendicular to one another. So we've just proved that the gradient vector is perpendicular to any level curve on the surface. Okay, well, let's put these properties to use. All right, looking at this, this says if the function is x squared plus 4y squared minus 16, and you can see it's this elliptic paraboloid. I've already graphed it for you. It asks us to find several things. First thing it asks us to find is the gradient of f at the point 2, 1. And so I can go through and find my gradient by doing my partial derivatives. So my gradient, the general form of my gradient, would be the partial with respect to x, that would give me 2x, and the partial with respect to y, which would be 8y. And substituting in the point 2, 1 gives us 4, 8. Now, if I want to sketch this gradient 2, 1 with the level curve of f through the point 2, 1, well, let's think about what that looks like. Okay, let's go back to the function real quick, and if I look at the function evaluated at the point 2, 1, I would get, plugging in 2, we get 4 plus, that would be 4 minus 16 gives us a value of negative 8. So looking at this, I'm sketching a level curve in here. Let's see if yellow shows up on here. That's at the value of negative 8. So we have some curve that falls in here that the level it's at is at negative 8, the z value that it's at. So that's our level curve. Now, what we want is we want that same thing to appear in 2 space. We want to see what that curve would look like. If we could just flatten it down to the xy plane, what would it look like? Well, it would be a curve that's equal to negative 8 at x squared plus 4y squared minus 16. So we would get 8 equals x squared plus 4y squared, which is an ellipse if we want to simplify this into, make it look like an elliptical form. We would get y squared over 2 plus x squared over 8 equals 1. So what that looks like for us, let me come over here. I guess I don't need that many dots along that line. Let's do them a little bit more spread out. Okay. If I were to graph that yellow ellipse on the xy plane, I know that it's going to have an x radius of root 8, and root 8 is just a bit more than 2. Don't know how much, but enough. And I know the y radius then would be the square root of 2, and the square root of 2 is just over 1. So we have an ellipse that looks something like this. Now, the point we're concerned with is the point 2, 1. And that point should be on our ellipse right here. And if we are to graph the gradient is the vector 4, 8. So from this point, I would move over 4. 1, 2, 3, 4. And I would go up 8 to 1, 2, 3, 4, 5, 6, 7, 8. And so my point would be right here. And if I were to draw a relatively straight line to that point, what we can see is that this line is my gradient at the point 2, 1, and that gradient is perpendicular to the level curve at that point. Now, if I want to find my direction of max increase at this point, I already know what my gradient is. I know that the gradient at this point is 4, 8. So my direction of max increase is 4, 8. But that means we can also use any scalar multiple. So if you gave me the answer of 1, 2, that's correct as well because it's a scalar of 4, 8. Or you could even give me the unit vector 4 over root 80, 8 over root 80. That would be the direction of max increase as well. Now, if we talk about the max function increase and how much that is, the max function increase would be the magnitude of 4, 8, which would give me root 80. And when we talk about the units of this would be the units, whatever f, I'm glad I can spell, the units of f divided by the units of x and y. Ours didn't give us any units, but that's what it would look like. All right, see if you can figure out the direction of max decrease and the rate of change in that direction. Hopefully you didn't have to think too hard about the direction of the max decrease because the direction is just the opposite of the gradient we had at the point 2, 1. And so this would be the opposite of 4 and the opposite of 8. And again, any scalar of those. And then the max function decrease would be negative root 80, the opposite of 80. And that is the idea behind the gradient vector. So hit pause and see if you can work with the next example, the one dealing with temperature Celsius. All right, hopefully you had a chance to try this, and hopefully the first thing that you did was find your gradient. So let's find our gradient of the vector t. In general terms, the derivative with respect to x would be negative 8x. Derivative with respect to y is negative 2y. So let's find the gradient of t at the point 2, negative 3. 2 would give us negative 16. Negative 3 would give us positive 6. So my direction that I'm headed of max increase is in the direction of the vector negative 16, 6, or any scalar multiple of it. And then the rate of max increase is going to be the magnitude of the vector negative 16, 6, which is the square root of 16 squared plus 6 squared, or the square root of 292, or we're dealing with temperature. Most of us wouldn't offer up temperature as a square root. So we can simplify this as 17.09. And this would be in Celsius. And this would be per centimeter because the x and y values were in centimeters. So 17.09 Celsius per centimeter. All right, hit pause and try this last one. Okay, hopefully in doing this gradient, you get the equation negative 0.02x for the x component and negative 0.04y for the y component. And therefore the gradient at the point 6100, parentheses, is equal to negative 1.2, comma, negative 4. So this is my direction of max increase. And it asked for what is the maximum rate of change. And the maximum rate of change would be the magnitude of the vector negative 1.2, comma, negative 4. which would be, need my calculator, 17.44 or approximately 4.176. And now those units would be feet, 0.60. That's cool. There's no units for the height. Well, normally we would have units, but anyway, that is the process of the gradient and the directional derivatives. Hope you have a good day.